Hello and welcome. In this video, we're going to look at the concept of local linearity and the differential. So you may recall that from Calculus 1, when we looked at a function of one variable, local linearity basically meant that if we zoomed in close enough on any function or any portion of the function, that what we would start to see is something that looks like a straight line. So this function here clearly is not a straight line. However, if you were to isolate one particular point, let's say we went ahead and focused on looking at this point here, or at least a small region around this point. So what we're going to do is we're going to kind of blow up that image. We're going to really zoom in on that portion, and what we're going to see is this representation right here. Now there's nothing unique to this particular point. We just happened to pick one of the points, and we can see that if you were to really zoom in, you would see a positively sloped line. Now a similar kind of context would hold if you were to zoom in on, say, the minimum of a graph, which we know that the minimum of a graph has a derivative of 0. So what we would likely see here is more of a flat line. And again, you'd have to zoom in pretty far, but when we talk about tangent slopes, what we're really saying is that in a local neighborhood, the function itself appears to be linear. Now that's a nice property that functions have, and it doesn't matter what kind of function we look. Now here, you can see here that this function is pretty straight here just by over a long interval, whereas in this little interval here we can see that that function does curve, but if you zoom in on any one point, you should see a straight line. The property of a function being linear in a zoomed in location is called local linearity. Now what we really mean by local kind of depends on the function itself. If you have functions that say exhibit a lot of erratic behavior, then local linearity may require you to zoom in on an infinitesimally small portion to be able to see the linear segment of that function. So local is this sort of double quoted word, which local can kind of vary from function to function, but if you have neater functions, like one that maybe looks like this, you can see that there's a bigger neighborhood in which the function appears to be linear. So when we think about this line, we may ask ourselves, well, what equation may model this line? And we do this for a number of reasons. One, for estimation purposes. If we fit a function to some data, and maybe that point right there represents the last data collection point, we can use the slope at that instant to predict what's going to happen a little bit later on. So with things like regression models that you might have seen before. So let's take a look at the equation of this function. It's a quartic function. This guy is quartic. It's fourth order. And if we wanted to compute the line that is tangent, or in other words, the equation of this line right here, when we zoom in on a really tight interval on the x and on the y, then the first thing we would want to do is actually get the slope at that point. And the way we do that is by computing the derivative. Right? So the derivative, or f prime of x, is going to equal 4x cubed minus 6x plus 2. Now this is the slope function. This function generates slopes. That's what a derivative does, or at least one of the ways we can think about what it does. And so now if we want to know the slope at x equals 0, so we're interested in the point (0, -1. And that's just from our illustration back here. We really wanted to focus on the point along that curve at 0, -1. So now that we have the slope function, now we actually need to gather the slope at this x value of 0. So to compute the slope at x equals 0, we need to compute f prime of 0, which comes out to, as you're putting in 0 for x, we get 2, which seems to make sense. It's a positive number. We see up here in the graph that the function exhibits a positively sloped line within a neighborhood of around x equals 0. And now that we have a slope and we want to fit a line to this, well, we know that a line takes on the shape given by y equals slope times x plus some vertical intercept. And so we know now that the slope of that line is going to be 2. So we can say that y is equal to 2x plus b. But we don't yet know what vertical intercept this should have. In other words, where would this line actually cross? The y-axis. Well, it's pretty evident here that it's going to cross at the point 0, -1. But in the way we've found linear functions in the past is to satisfy the condition that 0, -1 is a point along that line. We now have to say, plug in -1 for y, 0 for x, and we see kind of trivially here that b is equal to -1 because that point that we happened to pick was the vertical intercept of the original function. So now our tangent line is the function y equals 2x minus 1. And that seems reasonable. We can confirm, in fact, that this line does go through 0, -1, and that if we computed a rise-to-run ratio, that this should be a rise-to-run ratio of 2 to 1. And that's how we did this in Calculus 1. Now in 3 dimensions we have a similar analogy. In 3 dimensions, if we zoom in not on a function in 2 dimensions, but if we zoom in on a function in 3 dimensions, so here we have this paraboloid, and if we kind of pick the center point, we want to zoom in on it, and we do one zoom iteration on just that portion of this this little surface here. If we start to zoom in on that, then we get this shape here, which is slightly less concave and a little more flat. But now if we continue to zoom in, and we zoom in on this portion right here, and now that becomes this image, then what we see is something that starts to look even more flat than before. So intuitively, as you might guess, if we continued to do this, if we zoomed in on something like that little square there and blew up that image, what we would see is something that looks almost perfectly planar. So local linearity in 3 dimensions is if you zoom in on a point of any surface, if you zoom in far enough, what you should see is a plane. And we can also see that by looking at the contour plot. The contour plot of this paraboloid is not going to be linear. So we can see all the different, these aren't labeled, but we can see that there's definitely a lot of nonlinear change in our function. But then when we zoomed in from here to here, now we get these contours that are still curved, but they are slightly less curved. And then eventually, once we zoom in enough, we get something where the contour lines are equally spaced. Now, we could also look at a table of values. So if we focused on near the point, here's just some function x squared plus y cubed, and we looked at this function near the point 2, 1. So when x is 2, y is 1, we see that the z value is 5. So 2 squared plus 1 cubed is 5. And now we see that right around, as x changes by 1 and y changes by 1, we're not going to see much consistency in the rate of change. So if x changes by 1, we see that z changes by 3. But if x changes from 2 to 3, z changes by 5. So that's clearly not a linear change. And same thing going this way. This change represents an increase of 1 in the z value by changing y from 0 to 1. But when we change y from 1 to 2, we have an increase in z of 7 units. So if we zoom in, and what that really means is that we start to look at finer and finer increments. So instead of having 1 unit change in x, we're going to have 0.1 in changes in both the x and y direction. And here we can kind of see that this is about a change of just a little under 0.4. And the same thing happens here. This is about a change of pretty close to 0.4. But when we zoom in a little bit further, where our x values are spaced by 0.01, now we can really see that 4.93 to 4.97, that's a change of 0.04. That is z increased by 0.04 units by changing x by 0.01 units. And actually, that's exactly the same value here. 4.97 to 5.01 represents a change in z of 0.04 units. When we go the other direction, as y increases by 0.01 units, we see that z increases by 0.03 units. And when y goes from 1 to 1.01, we again see that z changes by 0.03 units. So the fact that now, and we can go across any row and see that that's going to be 0.03, and there's 0.03, and also going down any column, we should see that that's a change of 0.04, 0.04, 0.04, and 0.04. So locally, near 2, 1, we could say near the point 2, 1, it appears as though the partial derivative, which is what we're really getting at here, that is the change in z with respect to a change in x, at the point 2, 1, we could say it's pretty close, or we're pretty reasonably to say that if we increase x by 0.01, so the change in x, remember this means change in x right here, and change in z, so if the change in x is 0.01, the change in z was 0.04. And so that's a slope of 4. So every time x increases by 1 unit, we would estimate that z would increase by about 4, based on that local linearity approximation. Now, in the y direction, so that's going to be f sub y 2, 1, that when we change y by 0.01, we get a z change of 0.03, which is a slope of 3. So we would interpret this as saying, theoretically, if the rate of change were to remain constant, then increasing our y value by 1 unit would produce a change in z of 3 units. And of course, we see that that's not the case. Just like with our linear function back here, if we used the equation of this line to make predictions, let's say at x equals 0, well, we're going to get pretty similar values, because that is, x equals 0 is actually the specific point that we're looking at. But if we start to stray away from x equals 0, and let's say back up here we wanted to look at x equals 1, the exact output would be what the function would produce, which is f of x. So f of x, f of 1, would produce, let's see, 1 minus 3 plus 2. 1 minus 3 plus 2 is 0, and it produces a value of -1. So that's this value here. Happens to be the same y value. Now, what would be my approximation? Well, my approximation would come from the tangent line equation, which is y equals 2x minus 1. So y is equal to 2 times the value of x minus 1, which produces y equals +1. And you can see that there's evidently, or very clearly, these are not the same. This is the exact value, this is our approximation, and you can see we're off by a whole lot there. So the farther away we move from that x value, and trying to use a linear function will become a worse and worse idea. In fact, you can see that what's happened here is that we predicted an output of 1, but our actual function produces a -1. So we produced 1, 1. Our function, in actuality, produced 1, -1. And you can see that the farther away we move, the bigger the discrepancy between the value our line produces and the value our actual equation produces start to differ. Which is exactly the same thing we're seeing in our approximation here. We see that when x goes from 1 to 2, the z value changes by 3, which is pretty close to 4. And when y increases by 1, we actually get a z value increase of +7, which is a lot different than the 3 that we're estimating. So what's going to happen is the exact analogy of our curve. Our curve may look like this, and then we try to approximate a line, say at this point right here, and the farther away we move, the bigger that error grows. So that error starts to get bigger and bigger. Now sometimes they may come back together again and you may be right for like an instant. That is at the time that this curve comes up and this line intersects that curve. Then there might be some points where they're closer, but in general that error can be pretty unpredictable if we're using a line. You can see that here we're going to start undershooting. With a tangent plane, it's the same principle. We have some sort of point here, and we're going to denote that point by the location A, comma, B. So inside of this xy plane here, there's this point down here, which is just the projection of this point. This is the location A, comma, B. And then we have some sort of output value, some sort of z value associated with it. Our actual surface, that's this, in this case the paraboloid, is some function, z equals f of x, y. And then our tangent plane will be some plane that is tangent to this paraboloid just at that one location. And again, the farther we get away from that point in any direction, whether we go this way, or this way, or this way, or this way, the farther away we get from that point, the worse our approximation of the surface output is. So if I wanted to predict that output right there, you can see that we're going to way overshoot it in the approximation using our tangent plane. Now to construct this or put this all together, there are a couple of things we need to know. Well, if we're talking about a linear function or the equation of a plane has the equation z equals mx plus ny plus some z-intercept. Now the components of this equation are actually going to be some values that we can take away from what we know about partial derivatives. So if we think about what this value right here represents, that's going to be some change in z associated with a unit change in x. So for example, if I know that I earn, let's say, $10 per 1 hour, and I work for 10 hours, that's, in other words, my change in time, or this is in this case, the total time, and this is how much the change in my income would be for every 1 hour, then we can see that this is a slope. This is like m, and this is, in this case, like our input, x. And so the units that we end up with, we multiply these, is total dollars, which will be $100. So what approximation do we have for the slope in the x direction? Well, the best approximation that we know of, or that we can think of, is f sub x at that point. Okay? Or you could write it alternatively as df dx at the point a comma b, but we're going to go ahead and stick with the function notation version. And how do we think about that in this graph? Well, that's going to be our estimate of, at that point, if we were to change x by 1 unit, how much would z change by? So that's going to be going in this direction. We want to know what's the slope of that little vector right there. N is, in a similar sense, if that would have to be, some sort of hours in dollars per hour. Maybe I have a second job and I make $12 per hour here. I'd still have to multiply it by the number of hours. So this still has to be a rate of change. And since this is going to be the change in z per unit change in y, that's going to be f sub y of a comma b. And the way we can visualize that in this graph is that's the vector that is pointing towards the y-axis. And that's going to be our change in z associated with a 1 unit change in y. Now you can see that that's basically going to form the two slopes of our plane. And so our equation of this plane is going to be, let's see here, putting this all together, we're going to have our approximation of this function. So since the surface is actually called f of xy, our approximation of that surface near the point a comma b is going to be, or let's write it this way. our approximation of this overall surface, basically we could approximate it anywhere, but the further away from that location that we get, like we saw here, we're going to aggregate a lot more error. So we can just say that f of x, y, we can say it's approximately equal to the equation of the plane near that point AB times x plus f sub y at AB multiplied by y plus some some z-intercept rather. And that's going to be how we're going to write the equation of the plane. So let's take a look at this particular example. So at the point 3, 4, if we think about A being 3 and B being 4, then first of all, in order to estimate this paraboloid at that point, I would need the partial derivatives. I would need to know what the slopes are in the x and y directions. So the general slope is going to be the derivative of this function, which is 2x, and f sub y at the point xy is going to be x squared, its derivative is 0, y squared's derivative is 2y, holding x constant. And now we can go ahead and approximate these. So now we want f sub x at the point 3, 4, and that's going to give us 6. This equation doesn't depend on y, but there's no reason you couldn't write 0y if you wanted to. And for our second function here, f sub y at that point, how much z will change by per 1 unit change in y at 3, 4 is going to be 8. So far we have pretty much the big tidbits of how to put this equation together. So now we're going to approximate, and we do have to use the approximately equal to sign because f of xy is actually given by the equation x squared plus y squared. We're just trying to approximate it. And so this is going to come out to, let's see, it's going to be 6 times x. That's this, how much z change we get for every 1 unit x multiplied by how many units of x we have. Again, just like dollars per hour times the number of hours, plus 8y plus some z-intercept b. Now, much like we've been finding equations of planes in the past, we now have to get an estimate of b. So what we would need is some potential value for f for some x and some y. Now the point that we know that's going to be on this plane is given by knowing what f of 3, 4 is. So what is the z value when x is 3 and y is 4? Not what is the change in the z value, but what is the z value? And that's simply going to be 3 squared plus 4 squared, which is 25. So I have this ordered triple 3, 4, 25 that I know is on my plane. So I'm going to use that to help me find the value of b. I'm going to put in 25 here, put in 3 for x, put in 4 for y, and isolate the value of b. And if I do that, I am going to get a b value of negative 25. So our final approximation to f of xy near the point 3, 4 is given by f of xy is approximately equal to 6x plus 8y minus 25. And that's the final equation of our plane at that point. So in the picture above, where we saw the plane, we can sort of think about we just found the equation of this guy here, which is an approximation to the plane near the point A equals 3, B equals 4. There's also one other way to write this, and sometimes this is more of a convenient way. If rather than to have to go through all of the algebra, it is possible to show pretty easily that you can rewrite our mx plus ny plus b equation in this following format. This may look a lot like point slope form from linear functions. Just to show that we get the same answer, this requires the point a comma b, which we know is 25. That was at the location where a was 3, b was 4. f sub x at AB was 6. And then our x minus a in this case, well, x minus the a value, which is 3, plus f sub y at AB, which is 8, times y minus 4, we're going to argue that this is exactly the same equation. And let's check it out for a second here. So this will be 25. If we distribute the 6, we have plus 6x minus 18. If we distribute the 8, we'd have plus 8y minus 32. And if we combine like terms, 25, negative 18, negative 32, well, these add up to negative 50. Negative 50 plus 25 is negative 25. So you can see we get exactly the same thing. A lot of times we use this form, but it's kind of something you have to remember. So if you have to have an extra thing to remember, it's better just to go with something that you already do remember. Or look it up, of course. Now, to compare, or to kind of do a little bit of an error analysis, we said we're focusing on this paraboloid, or a better looking paraboloid. Let's try this again. So we're looking at this point. We have these axes. We're looking at this point at 3, 4. And that's actually some point on that surface. But now we're approximating that with a plane, and we want to know how well does the plane perform. We've already come up with our approximation to this function as being 6x plus 8y minus 25. And so what we want to do is we want to estimate f of 2.9 comma 4.2. So if we estimate this value, we calculate f of 2.9 comma 4.2. That is plugging 2.9 here, plugging 4.2 there. We get our approximation of 26. Now, the exact value is going to be the value that actually comes out of the original function. That is this guy right here. So the exact value, and that's the exact value can be visualized as the output along this surface. That's this actual point right there. So f of 2.9 comma 4.2. Now I don't have to use the approximately equal sign anymore because now I'm going to plug it in up here. Equals 2.9 squared plus 4.2 squared, which comes out to 26.05. And you can see here that the error is only 0.05 units of error. And that's not bad. So our function does a good job of approximating points near the location 3, 4. But how does it do if you go a little bit further? So 2, 2 is some other point over here. We'll say that right there would be the point 2, 2, and that's going to correspond to some point along the surface. How well does our plane do now? Well, let's again try our estimate. Our estimate is going to come from our linear function. F of 2, 2 is predicted to be approximately, putting in 2 for x here, 2 for y here, subtracting 25, we come up with a z-value of 3. Now, if I compute the exact value, the value that's coming from the equation of the paraboloid, f of 2, 2 actually comes out to be exactly 8. And so now we can evidently see that the error is 5 units of error. And that's huge. That's huge. So this is why we call things local, because the equation of the plane will only really approximate values locally for that paraboloid, or for any other function for that matter. Now, how fast these approximations diverge from the exact value is a matter of how complex or how erratic the function is that we're dealing with. A paraboloid is not super erratic, but it does have rates of change that do grow change very quickly. So one other way to visualize this is here we have some portion of a surface. So this picture here is going to be our exact. This is going to be our exact curve right here. That's just some portion of a surface. And the plane below it is our approximation for that surface. So this is our tangent plane. Okay, so the true value of f of xy is some point there. And if we use our plane to approximate it, we're going to get some point there. And the distance between them, the distance between them represents the amount of error that we get. So this is all error. We are undershooting our value, in this case by what appears to be a fairly large amount. Now, how do we write the equation of this plane in terms of what we know so far? Well, we know that the equation of our plane looks like this in the alternative form that we're allowed to list it in. And here, again, we're approximating the surface, the true surface, by grabbing instantaneous rates of change and putting them together in this following form. Now, the way we can think about the distance between our a value, the actual point that we're approximating at, which is likely somewhere over here where the tangent plane actually touches the surface, then how far we move from that location. Well, actually, we'll just say that point is here in the corner to make this visually a little bit easier. So here I have the point that I was actually trying to approximate. And now over here at the location that I'm trying to use my plane to approximate the surface at, which clearly has this big error, that represents a distance, a change in x relative to the point A. Well, that's exactly what this is. This is the change in x relative to the point A comma B. So in other words, that's just how far away we are from this point A comma B. And that's going to be characterized by this distance right here. That's the change in x right there. That's how far we've moved in the x direction from the point A comma B. In a very similar sense, when we think about how far we are in the y direction, that's our change in y right there. And that again is just change in y relative to the point A comma B. So that's characterized by this segment over here, which I'll just go ahead and draw on this side. That's the change in y right there. So we see that that's the change in y. That's along this side, but it's hidden behind our surfaces there. So this right here is also the change in y. So what I'm really doing is to compute f of x comma y. To estimate that, it's f of a comma b, the actual z value at the original point, plus the rate of change at that original point, multiplied by how far we go in the x direction, plus the rate of change in the y direction at our point of interest, multiplied by how much our change in y is. Now we're going to come back to this format here shortly, but I just wanted to make the connection that x minus a and y minus b can just really be thought of as how far you stray away from the original point, to give a little bit of intuition behind that process. Let's take a look at one more example before we do make this final connection. Here we have a problem about designing safe boilers. And designing them depends on knowing how steam behaves under changes in temperature and pressure. Steam tables, such as table 14.6, which is this one here, are published giving values of the function v equals f of t comma p, where v, the values listed inside the table here, are the volumes in cubic feet of 1 pound of steam at a temperature of T in degrees Fahrenheit. So these are the temperatures that we have. And P, which is the pressure in pounds per square inch. So how many pounds of pressure per square inch there are, what the temperature is, will determine how 1 pound of steam, the volume of 1 pound of steam. So let's see what happens. As we can see that at the lowest temperature setting, at the lowest pressure, we have a volume of 27.85 cubic feet. So it looks like as we increase the temperature for 20 pounds of pressure, it looks like the volume of 1 pound of steam increases. And that seems to be the case for every pressure level. As you increase temperature, it looks like in general the volume of 1 pound of steam increases. Now, if you keep the temperature fixed and you look at changes in pressure, we can see that there's actually a drop in volume as you increase the pressure. I'm not a chemist by any means, but I imagine that's because as there is more pressure, it causes those that same volume to not have to take up as much space. And so here we can also see the same thing, that as pressure increases for a fixed temperature of 500 degrees, the volume of that 1 pound of steam drops off. So we want to estimate. We want to create an estimate for this function. Now here's where this linearization, or this local linearization, comes in handy, because we don't actually have a function for this table. So as long as we assume some local linearity, we can actually build a function for this near 500 degrees Fahrenheit and P near 24 pounds per square inch. So to identify where that point is, 500 degrees and 24 pounds per square inch, we're looking at this cell right here. So in order to approximate f of t comma p, get a function for it, we know that that's going to be f at our point, which in this case near 524 pounds per square inch of pressure, plus the rate of change in one of the directions. So since t is like our x, we'll say f sub t. So how much does the volume change by per unit change in temperature, approximated at 524, multiplied by the difference between the temperature and 500. So that's our a value, t minus our a value, plus f sub p at 500, 24, multiplied by the difference, the change in our pressure relative to 24, so p minus 24. And so we of course need some approximations here. We need to get f sub t, which is going to be this guy here. And we also need to get f sub p, which is this guy right here. So we know how to approximate that from tables. One possible way of doing this, of course there are many ways to approximate these numerically, but one such way is to say that f sub t at temperature of 500, pressure of 24, is going to approximately be equal to, well, if I want to know what happens when I change the temperature, so if I change the temperature to 520, I basically want to ask, okay, well, what's the difference between our volume at the new temperature, holding the pressure fixed, and the difference between that and the volume at 500 degrees with the pressure still at 24, divided by how much we changed the temperature by. So in this case, the temperature went from 500 to 520, so 520 minus 500 will give us that positive 20 units of increase. So we'll have 20 degrees Fahrenheit of change, and we see that this is going to be 24.2 minus 23.69, and that is in cubic feet, which comes out to about 0.0255, and this is going to be cubic feet of volume per 1 degree Fahrenheit. So we did indeed see that as you increase the temperature holding pressure fixed, you do get an increase in the volume. Now we're going to do the same thing for f sub p at 500, 24, but now we're going to hold the temperature fixed and only change the pressure from 24 to 26. So that means that we need to look at holding, in both cases, the temperature fixed. We need to look at the volume at 26 pounds per square inch of pressure and at 24 pounds per square inch of pressure, divided by the change in the pressure, which is went from 24 to 26, a change of 2 units. So that's going to be 2, we'll just write this pounds per square inch, PSI. And up here, this is going to take the difference between 21.86 and 23.69. It's still in cubic feet. We're looking at the change in volume. And this is going to come out to negative 0.915 cubic feet per 1 degree, per 1 PSI. So in this case, we do see that as you increase pressure, holding temperature constant, you do get a drop in the volume of the 1 pound of steam. And now we can put this all together. We can say that F of T comma P is our F of 500 comma 24. Well, that's just the actual volume at that temperature and that pressure. So we're estimating this function, so we're going to use approximately equal to. And remember, the reason we're putting this is not because we approximated the 2 slopes, but because we're trying to approximate the function based on just utilizing 1 point. So how this surface would actually look, whether this would look, like this, we have no idea what that surface looks like. We could plot these points and try to approximate it, but we're going to approximate the function v equals f of tp with this linearization. So f of 500 comma 24, we know that that's 23.69. So we have 23.69 plus what we just approximated for the change in volume per change in temperature, is 0.0255 multiplied by how much your temperature is going to change by relative to the original temperature of 500 degrees, minus 0.915 times P minus 24, or our change in P. So remember, this right here represents our change in T relative to 500 degrees, and this right here represents the change in pressure relative to 500 degrees. Now, we can answer questions about this. We can say, well, estimate the volume of a pound of steam at a temperature of 505 degrees Fahrenheit and 24.3 pounds per square inch. So we don't have that. We don't have that information. 505 is somewhere between 500 and 520. 24.3 is just a little more than our value. So we're talking about a point that would hypothetically lie somewhere right there if this were our two-dimensional plane. So the linearization allows us to do this quite nicely. So to estimate f of 505 comma 23.4, or rather 24.3, to estimate that value, now I can plug it into my linearization. So I'm going to put in 505 for the t here. I'm going to put in 24.3 for the p value here. And once all that is said and done, I'm going to say that for that temperature and that pressure, we're talking about 23.54 cubic feet of volume. Now let's see how reasonable that is. Well, first of all, 23.69 was our volume, our exact volume for 500 degrees and 24 pounds of pressure. We increased the volume, we increased the temperature by 5 degrees, and so we know that we get an increase in volume for every 1 degree, but then we increased the pressure by 0.3 pounds per square inch, and every 1 pound per square inch actually reduces the volume. But since we increased this by a lot more than we did this, we see that the volume actually did go down a little bit because we're taking a small difference, but 0.0255 is much smaller than negative 0.915. So even if you multiply this by 5 degrees of change, remember this right here would be 505 minus 500 would actually represent 5 degrees Fahrenheit change. P minus 24 would represent a 0.3 PSI increase. And so when you multiply negative 0.915 by a third, that's still going to be bigger than 0.0255 multiplied by 5 degrees Fahrenheit. Now our last and final concept is this idea of a differential. Not quite like a differential equation, but they are related quite so. Now, a differential is often described as df or dz, and at a point AB is the linear function of dx and dy given by this formula here. df equals the slope in the x direction, dx, plus the slope in the y direction, dy. Now, where on earth did this come from? Well, the good news is that if we look back at this function and we analyze this a little bit more, we can see that these two are actually related. Let's see how. So we've already described that this right here represents the change in x, and that this right here represents the change in y. Now, if I actually do one more thing here and I subtract over the f of a, b, I get f of x comma y minus f of a comma b is approximately equal to f sub x at ab times delta x plus f sub y at ab times delta y. Now, what is this quantity over here? Well, if I look at my actual point, so I'm going to jump back up here real quick to our last picture. This was the true value of f of xy. So f of xy is the true value. This right here is our approximate value. And when we take the difference between them, this represents the change in our f. I'll just write it as change in f. You could write it as change in f of xy. And that's approximately f sub x at a comma b times delta x plus f sub y at ab times delta y. Now, as I make delta x and delta y as delta x and delta y both approach 0, then this becomes dx. This would become dx. This right here would become dy. And delta f would become delta f. Or df, excuse me. Delta f would become df. And so, in conclusion, we have that df, and now we can say is exactly equal to, because we're basically saying if you don't stray far away from the point of interest, a comma b, if the point that you're estimating at is very, very, very close to the point that you linearized at, then we're saying that the change in f is actually exactly equal to f sub x at the point a comma b dx plus f sub y at the point a comma b dy. And we can see that this and this are exactly identical. So this is just called the differential, and what it actually does tell us is that the actual instantaneous change in f by observing the change in x and the change in y as being infinitesimally small. Of course, we have to multiply, if this is dollars per hour, we have to multiply that by how many hours, and if this is dollars per hour, we multiply it by hours, then we get total change in dollars. So we can actually compute the differential of a function, which is quite convenient or useful in later applications. So in order to do this, we really just need the two partials. So f sub x of x comma y is equal to, that's going to be equal to, well, holding, in this case, y constant, the derivative of x squared is 2x, so we get 2x e to the 5y. And f sub y, the derivative with respect to y, holding x constant, so x squared, the derivative of e to the 5y with respect to y is e to the 5y, times the derivative of 5y, which is 5. And so now I can put this into differential form. Now this did describe a point, that we have some sort of point, but there's also this statement that says the differential at a general point is often written as df equals f sub x times dx plus f sub y times dy. So to write our differential, df, we can say that that is f sub x, 2x e to the 5y, times dx plus f sub y, which is 5x squared e to the 5y multiplied by dy. And so our differential of that equation is this guy right here. So that really concludes our topic here. To summarize, what we've established is reviewing back from our earlier calculus days, we could calculate the tangent line to a curve, and essentially what we were really doing there is creating a locally linear approximation of the function at our point. We extended that to saying if you zoom in on any three-dimensional function, the closer and closer and closer you zoom into a specific point, the more you're going to see the representation of a plane, both in the surface itself and as well as in the contour plots. And also in table form, we can see that the more we zoom in and the smaller increments in x and y that we get, eventually we see something that resembles a plane. Then we explored how to build that function. We built it two ways, by understanding, first of all, that a plane has this form here, z equals mx plus ny plus b, and then by saying that really our m and n are our two partial derivatives, to building up to this more general form that we showed that these two generate the same equation, and continually building that up until we get to this thing called the differential. So that is all. I hope this has been helpful.